Inside our bodies are defenses infinitely more complex than anything man has invented. The immune system is what protects us from disease. Now, biotechnology is trying to manipulate that system, seeking to detect, prevent, or wipe out disease by taking part in the body's never-ending cell wars. Every cell in our body is constantly preyed upon by intruders, like this virus. Once inside a cell, each predator breeds hidden battalions of disease. Fortunately, they betray their whereabouts. Part of their protein coat stands out on the cell's surface. This antigen is spotted by defenders. This is a macrophage. It patrols the body looking for trouble. If it finds anything unusual, such as a cell displaying an antigen, it eats it. But see how the antigen now appears on the surface of the macrophage. Another defender uses the antigen to home in on the macrophage. This is the all-important helper cell. They can land directly on infected cells, too. The helpers secrete a chemical which musters killer cells. Another helper chemical primes the killer cells for battle. The killer zeroes in on an antigen to eliminate the diseased cell. Chemical signals also mobilize antibodies, the interceptor missiles of our immune system. Antibodies come in many guises, each one fitting like a lock and key with one particular protein. Remember, viruses have a protein coat. That's what the antibody latches onto. It stops the virus in its tracks and so protects us from disease. of exploiting the immune system that we're all familiar with is the use of vaccine. By, in effect, giving ourselves a small dose of a disease, the immune system can rehearse its response. Should the disease later attack in earnest, all the defenses are primed and ready to overcome it. In this way, we can protect ourselves from a large number of diseases, because the immune system works equally well against bacteria as against viruses. Sometimes the immune system can be a problem when it overreacts to cause allergies. Lauren Dalglish reacts so severely to the protein content of dust that she must take great care to avoid ever breathing it in. Dining out can be hazardous when anything on the menu might contain ingredients that could endanger your life. Lauren sticks to places where the chef understands that she doesn't want her candlelit evening to end in the emergency room. All this because antibodies are recognizing particular proteins and treating them like the enemy.
It is done on tomato base, so there's no dairy products at all in that too.
The fact that antibodies are so specific, one antibody fitting only one protein, makes them of great interest to medicine, especially since biotechnology has learned how to isolate them and multiply or clone them outside the body. Starting with just one of the B cells which produce antibodies, a British company, Celltech, can clone billions of identical antibodies every day. So-called monoclonal antibodies like these are already transforming medicine. Many of the products of biotechnology are still in the development stage. Others have been frozen by regulatory delays or legal battles. But monoclonal antibodies are in the stores today. By detecting the presence in the body of proteins we secrete at different times, monoclonals permit us to carry out reliable diagnostic tests in the privacy of our homes. In hospitals, an increasing number of diagnoses are being performed this way. But the medical applications of monoclonal antibodies only begin with diagnosis. Now they are beginning to be used in the treatment of disease. Brian Quinn has leukemia, cancer of the blood. The best hope of curing it is to destroy his bone marrow, in which blood cells are produced, with massive doses of radiation. Then it can be replaced with marrow from a donor. Brian is lucky. Having a brother, his chances of getting marrow that will suit him are 1 in 4. People without a brother or sister have only one chance in tens of thousands. The problems don't end with finding the right marrow. Even if Brian's body accepts the marrow harvested from his brother, there is a danger that immune system cells imported with the marrow will attack him. This potentially fatal reaction can be fought with drugs which suppress the immune system. But this, in turn, makes the patient powerless against infection.
Now, we developed a different method of tackling this disease, and that is to use monoclonal antibodies. Now, monoclonal antibodies are very pure antibodies that can be directed highly specifically against target cells. And what we do is to use monoclonal antibodies to destroy cells in the donor marrow that can cause this reaction.
A centrifuge removes the white cells from the donor marrow. Among them are the helpers and killers, more scientifically called T lymphocytes. It is these T cells that might attack Brian. So monoclonals that seek out and destroy the T cells are added to the marrow. As a result, the incidence of bad reactions has been reduced.
It usually happens in up to 70% of transplants between brothers and sisters. But with the use of monoclonal antibodies, we can reduce this complication to 20%, and we reduce fatalities from around 20% down to 0.
Brian can now receive the marrow, which the monoclonals have purged of T lymphocytes. But cell wars are never straightforward. The new technique prevents the marrow attacking its host, but the chance of the host rejecting the marrow went up.
With conventional bone marrow transplant, without the use of monoclonal antibodies, the risk of a leukemia patient rejecting the marrow was very low, maybe 1%. When we started to use T lymphocyte depleted marrow with monoclonal antibodies, then that risk went up to 12%. Now, that problem has been overcome, firstly by recognizing it as a problem, and then subsequently by increasing the drug and radiation treatment prior to the transplant. So that's really no longer a problem. If we're using a donor who isn't fully matched, then we have to use further methods to reduce the patient's immunity. And in fact, one of the ways we do that is to give the patient monoclonal antibodies nowadays. So we're using it both to treat the marrow and to treat the patient. The residual problems in bone marrow transplant now appear to be those of infection. If we can solve these problems, we anticipate that we'll be curing maybe 80 or 90% of patients with bone marrow transplant in the near future. At the present time, our cure rate is around 65 to 70%.
At London's Charing Cross Hospital, monoclonal antibodies are at the heart of a new method of detecting cancer with astonishing accuracy. Many of the patients who come here have cancers that conventional scans have failed to pinpoint.
This is a lady with a type of cancer which produces a hormone which enables us to distinguish it from normal parts of the body. We've measured the hormone in her bloodstream and shown that there is some cancer somewhere in the body, but we can't tell where it is. We need to find it to see whether it can be removed because it is not responding to the drug treatment which usually helps this condition. So we have attached radioactivity to a monoclonal antibody which binds to the hormone, and we gave that into her bloodstream yesterday, and today we will hope to see some concentration of the antibody in the tumor, and that way we can find it by using a gamma camera which makes a map of the radioactivity in her body.
Cancers produce hormones. Hormones are proteins. So a matching monoclonal can be made to carry a radioactive molecule to them, like a microscopic torchbearer.
That technetium on the right, is it? These pictures show the sort of images that we get here. The red color shows you where there's more radioactivity, and you can see that it's concentrated here in the lower part of the abdomen. Now, the ordinary scans of the uterus have not shown any sign of tumor there, but we know that particularly in this site, this method can sometimes detect tumors that you can't detect by conventional scanning methods.
If the scan is to be of real use to the surgeon, you've got to do better than produce a flat image of the tumor's whereabouts.
Here you're just looking at a two-dimensional view. We can also use this machine to go round the patient and produce a three-dimensional picture so that we can produce pictures that look like slices through the patient at different levels. And that does give us a much better idea of where the tumor is located within the patient. So that is a significant advance in this.
Because they can be so precisely targeted, monoclonal antibodies have been heralded as a new breakthrough for cancer treatment. Some doctors are concerned that our present methods are more of a blunderbuss than a precision instrument.
The trouble with most drug treatments that we have at the moment is that they not only damage the tumor, but they damage normal tissues a great deal as well. Now, if we can use a monoclonal antibody to carry a treatment specifically to the tumor and much less to normal tissues, that would obviously be a very attractive approach.
Bijent's team has been treating patients with monoclonals armed with sufficient radiation to kill cancer cells. The camera shows they are hitting their target, but the results have been disappointing.
We haven't been able to get enough in at a single dose in order to get effective treatment against cancer. We have sometimes been able to give some pain relief to patients, but really the treatment is not as good as conventional methods just yet.
The problem is that each successive treatment seems to produce less of a response. We can see on the left of the screen how first time round the antibodies delivered their healing payloads successfully, in this case to a liver tumor. On the second attempt, there is much less concentration in the treatment area. Something is preventing the antibodies from homing in on their target. These are the unwitting culprits, the animals whose cells are cultured in the manufacture of monoclonals.
The majority of the monoclonals that we see entering into the biotechnology market today are made in mice. They're mouse or murine monoclonal antibodies. A limitation of the mouse monoclonals in the body, in humans, is that it is a foreign protein. It is mouse by nature, and therefore it's recognized in the human by the immune system as a foreign protein, and consequently the human responds by generating an antibody response against this mouse monoclonal. These antibodies are called HAMAs, human anti-mouse antibodies. And the HAMA response has become a major limitation in the use of mouse monoclonal antibodies in the body for therapeutic benefit.
Mice have lived alongside humans since we were both cave dwellers. Even in our sterile modern apartments, we can't escape them altogether, consuming microscopic fragments of mouse proteins in the cereals and grains we eat. As a result, our body's immune system generates antibodies to eject these intruding mouse proteins. If we are treated with monoclonals made in mice, our immune defenses can't tell friend from foe. They swing into action against the monoclonals and stop the treatment working. Richard Bijent is trying to overcome the HAMA syndrome by using drugs to weaken the patient's immune response before antibody treatment begins. Here, the first dose of antibody is binding to the tumor in the liver. Even after a fourth dose, it is still performing well.
We have been able to approximately double the time for which we can give antibodies compared with what we could do before. But we don't abolish the reaction completely, but that's our first step along this road, and it shows that provided those advances continue, we may well see something that is really beneficial to patients with cancer in a few years' time. A
biotech company in Maryland sees things a different way. If humans reject monoclonals made from mouse cells, why not make them from human cells instead? The problem is that cells don't like to live outside the body. To get around this, you have to give them cancer. This makes them live forever. The cancerous B cells are cultured and tested to see what kind of antibodies they produce. The useful ones then join the production line, living, feeding, and breeding at blood heat. Early trials with cancer patients suggest human monoclonals may work better. Certainly they have raised the hope that they will one day be the long-awaited magic bullet cancer cure.
I was very skeptical that there was going to be a magic bullet for cancer. I was even more skeptical when I began to see the early clinical results with the mouse monoclonal antibodies. On the other hand, I've got to tell you that I've become extraordinarily encouraged by virtue of watching our human monoclonal antibodies being used in colon cancer patients. Properly conjugated with a drug that would impact that tumor, I'm convinced that they're going to be able to be one very important arm of treatment of cancer.
In the 1980s, a new disease has launched a terrorist attack on the body's defenses.
At first, only gays and IV drug users were being killed by AIDS.
Immunology became dinner table conversation when AIDS became the most publicized disease of all time.
It could kill more Australians than World War II. If you have sex, have just one safe partner. Always use condoms.
Hey, Vicky, I've got a condom.
You know how to use it?
Sure.
Well, now all you need is someone to use it with.
You don't want me to wear this? Oh, come on, no.
And if he says no, so can you.
Forget it.
Come on.
Vær derfor kritisk ved valg av partner, og ha ikke seksuell omgang med hvem som helst. Faren for å bli smittet reduseres betraktelig ved bruk av kondom.
Anyone can get it, man or woman. So far it's been confined to small groups, but it's spreading. So protect yourself.
One of the reasons that the disease is so difficult to deal with is that we have had so little information about the human immune system before we began to see this new epidemic. So much of what we know about the system that's being damaged by AIDS, we've learned through the study of AIDS patients. So there's been a necessary slowdown in our work with working with the disease. In fact, the virus that causes AIDS is a very insidious one. It infects people years before we see any clinical evidence of disease. So by the time we see a patient, the immune system has been largely destroyed, and during that time, the person has been capable of infecting other people. So it's a very dangerous situation for the patient with the disease and also for the society dealing with this epidemic.
Like other viruses, AIDS infects cells. But AIDS is choosy. Its targets are the helper cells, the ones that mastermind the whole immune response. AIDS takes control. One day, maybe years from now, it will start to reproduce. When it does, the helper cell will be unable to coordinate the body's defensive arsenal. Like a terrorist, AIDS shuns uniforms, changing its appearance often. Antibody production can't keep up with this quick-change routine, and the infection spreads unchecked. San Francisco General Hospital holds a sad record. 1,800 visits per month from sufferers no longer able to resist invading microbes or cancerous growths within.
How have you been feeling today?
Oh, a little on the weather. Headache, a little bit of a fever this morning, maybe, 99 to maybe up to 100, and but the Tylenol seems to be keeping it down. It was running up to 102 last night, for about 2 hours.
Well, your blood pressure is good. It's 130/82.
Never had a problem with that.
Yeah. Okay, I'm going to listen to your heart now, so just breathe normally.
Diagnosis of an AIDS patient is, in fact, quite easy. The clinical problems that we see, the cancers are striking.
Let's just examine here and see. Do you have any new lesions coming up?
Yeah, we got one little bit here.
One group of cancers, the Kaposi sarcoma, are visible on the skin, so we can see that easily. The other major cancer that we see, the lymphomas, are explosive in their growth, so again, the disease isn't subtle. The problem is in finding the infection before the person has actual AIDS. That is very difficult if you rely on clinical evidence. Patients in that state before they develop AIDS, but after they're infected, often appear and feel perfectly normal.
Antibodies are crucial to the current AIDS test.
Okay, you can have a little.
The test can't find the virus itself, so it looks for other evidence. Antibodies which the immune system has managed to make against it.
So bad.
But this leaves loopholes for the disease to exploit.
The current test for the AIDS virus, HIV, human immunodeficiency virus, only measure the antibodies to the virus and not whether the virus is actually presently existing in the body. The problem that this results in is the fact that it takes approximately 6 weeks to 6 months for a person to develop antibodies to the virus infection. As a result, this test does not measure the first 6 to 6 months of infection. The second problem is that there will be some people who successfully resolve the infection. That is to say, they lose the virus because of the immune system. It will be important to determine which people have been exposed to the virus but no longer have it. And in addition to that, the existing antibody test will not be able to be used to monitor patients on various drug regimens or antiviral therapies, because it will be important to find out what's happening to the virus during that treatment rather than what's happening to the immune system.
When the AIDS virus attacks, it merges its own DNA with that of the cell. That DNA is the giveaway. But the problem is, only 1 in a million cells in a blood sample is likely to contain it. The test uses a combination of enzymes and rapid heating and cooling to increase the amount of DNA available. The needle in the haystack becomes a steel beam.
There are two reasons why we think that the test will be more efficient. One is because we will be identifying the virus itself, so we will be able to identify individuals very early in infection rather than waiting for antibodies to be mounted to the viral infection. And secondly, the virus has the ability to hide in cells, much like a Trojan horse. Our procedure has the ability to, in fact, look inside the cells for the nucleic acid, the hereditary material of the virus, even when it's not active within a cell, so that we have the ability to identify one infected cell among a million uninfected cells, even when that infected cell is, for all practical purposes, invisible to the immune system of the body.
Better diagnosis will be a great help. But can biotechnology also be of use in treating the disease?
Well, I can understand that. You've had your blood drawn quite a bit.
When we talk about treating people with established AIDS, what we will have to do probably is first treat them with an antiviral drug, a drug to inhibit the replication of the virus, and then follow that with an agent that might help boost the immune system and allow the immune system to recover. So that double type of therapy design is what we are looking at now.
The idea is to rally the immune system, using genetic engineering to manufacture the vital chemical signals, like interferons and interleukins, which cells damaged by AIDS no longer produce properly. Many consider the so-called biologic approach our best bet against AIDS.
This virus, one of the really awful things about this virus is that this group of viruses inserts its own genetic information into that of the host. So with conventional antiviral drugs like AZT, we do not expect that any of those will cure the virus infection. The virus will stay there. There is some hope that with biologic approaches, if we could find ways to get the body immunologically to recognize infected cells, that might be at least something to work for as a potentially even curative approach to this infection.
But in San Francisco, the first biotech drugs tested against AIDS have brought little comfort so far.
We treated approximately 90 patients on various doses of interleukin, and while the drug did not seem to cause any harm to the individuals, it didn't also seem to boost their immune system, which was what the theory was. The side effects were not very well tolerated at the very, very high doses. And high doses, we're talking about 1 and 2 million units per injection. The side effects that the patients had were very severe chills, shaking chills actually, with fevers, a lot of fatigue, just feeling like they're coming down with the flu. The other compound, alpha interferon, we've done a number of studies here at this institution. Some of the same side effects were seen as the patients who were on interleukin. So at the high doses, it's not clear if this medication would be efficacious by itself. It's very frustrating because each time a new drug comes out, you put your hopes into it. You think that, well, maybe this is the answer. Maybe now we'll take a big step in the right direction. And so far to this point, we've only made a lot of little steps. Even with the advent of zidovudine or AZT, we've only made a small step. But I think we are going in the right direction, and that is very exciting, very rewarding.
The best solution would be a vaccine. But the AIDS virus changes its character like flu, and there has never been a vaccine that could cope successfully with that disease. As well, vaccines are the poor relations of medicine. Only 20 have been developed in their 200-year history. For vaccines are miracles with flaws. Known since the time of the pharaohs, polio reached epidemic proportions in the early 1950s. Those were blighted summers, when even a rumor of the disease emptied main streets and left public meeting places deserted. Even the all-powerful DDT didn't stop the epidemic. But you had to do something. The American people declared war on the disease that had held them in thrall. Jonas Salk, funded by the March of Dimes, developed a vaccine. By 1954, tests showed it was effective. It stimulated the production of antibodies that neutralized polio viruses. Launched in 1955, the Salk vaccine wiped out polio in 7 years. It is one of the great success stories of medicine and one of the safest vaccines ever made. Even so, the vaccine paralyzed and killed some children. Vaccines against viral diseases are made from the viruses themselves. The immune system recognizes them and counters by producing antibodies. But the viruses must first be killed or weakened, and any mistake can have pitiful results. The genetic engineers promise to produce a range of risk-free vaccines. The first available now is for hepatitis B.
Hepatitis B is a rather bad disease. It's not a very prevalent disease in North America or Canada, but it's a tremendously bad disease around the world. And there are about 500 million people infected with hepatitis B virus. And it's a very debilitating disease, and actually a good % of them develop cancer, which is hepatocellular carcinoma. This disease is very bad, and there is a significant amount of people that died out of hepatitis.
It was known that the immune system's production of antibodies to protect against viral infections is triggered not by the whole virus, but by one small part of its protein coat, the antigen. The blueprint for every protein is a gene. Chiron set out to isolate the gene which made the hepatitis B antigen. If they could find it, they could splice the gene into easily grown microorganisms, bacteria, yeast, or fungi. They could mass produce the essential ingredient for a vaccine.
We isolated that gene that codes for the hepatitis B surface antigen protein. It's called the surface protein, and introduced it in a microorganism, in our case was yeast, that is able to produce this protein inside the yeast. So then we took this transformed yeast cell, this genetically engineered yeast cell, and make fermentations with it, and isolated the protein out of the yeast.
The antigen grown in yeast appeared in every way identical to an antigen found on a virus. But would it trigger antibodies? Would it have the power to vaccinate?
We did experiments in chimpanzees where we injected this particle and measured a high level of antibodies. Then later we challenged with the live virus, and all the chimpanzees that had been injected with this particle made in yeast did not get the disease. So at that time we knew we had a vaccine and did several clinical studies with humans. They injected more than 3,000 people with this vaccine, and in all cases the development of antibody was very good.
Fear of lawsuits resulting from the deficiencies of traditionally made vaccines has put vaccine development on the back burner for drug companies. Valenzuela hopes the new gene-spliced vaccines can overcome this, and resistance to genetic engineering.
Very few people believe in the new vaccines because there was not a lot of knowledge about recombinant DNA, and that's exactly what this vaccine can provide. An example that using recombinant DNA now, you can get a vaccine that is absolutely safe, a vaccine that is not made out of the virus itself, but is made of a tiny part of the virus in such a way that cannot give you the disease.
This is cancer, a primary tumor removed from the colon. Cancers kill 5 million people every year. The idea that you could one day be vaccinated against diseases like this seemed like a fairy tale. Until now.
This has always been a goal of immunologists, and it's always had an extraordinary attractiveness to immunologists because we certainly have seen vaccines work for other types of diseases. Why couldn't we generate vaccines that would work in cancer patients, such that when the primary tumor was removed, and when the patient is at a state of his disease where he has presumptive metastasis that may recur in 2 or 3 years and eventually kill that patient, why couldn't at that time we immunize the patient to his cancer, let his immune response seek out and destroy these microscopic beds of cancer cells wherever they are in the body, so that there is no recurrence and thus the patient is totally cured by the combination of surgery and immunotherapy.
After it has been removed, bionetics isolate the cancerous cells from the surrounding tissue in the patient's tumor. Just like viruses, cancer cells have antigens, which the immune system can recognize and attack. The idea is to render these cancer cells harmless and then put them back into the patient. This should stimulate the immune system to strengthen its forces and wait in readiness to attack any fresh outbreaks of the disease.
In the study that was just completed, which is a pilot study, we were able to show that by effective immunization compared to non-immunized controls, we had a 50% reduction in recurrence in colon cancer patients at 3 to 5 years after surgery. That is, we got half the expected recurrences that were predicted by the non-immunized control group. What's more, the quality of the recurrences were such that many of those patients that did recur in the immunized group were amenable to second surgeries, such that they were tumor-free at the time of their second surgery and are living longer, and thus there was a statistically improved difference in survival among the immunized versus the non-immunized patients.
As with viruses, you don't need whole cancer cells to make vaccine, just the antigens. Human monoclonal antibodies are helping to identify the antigens on the surface of tumor cells. This, it is hoped, will enable the gene splicers to progress from vaccines tailor-made for each patient to a vaccine suitable for everybody.
By taking these antibodies and simply probing the tumor cell, one can identify those particular foreign proteins. And then, through genetic engineering, one can create an abundant generic vaccine. We have identified 2 of these tumor antigens. We're not sure what the full matrix is going to be, but within the next decade, we should be at the point of having a generic vaccine that will be testable in at least colon cancer, the second major disease of man that up till now chemotherapy had failed in, and surgery was the only treatment that was recommended for this disease.
So biotechnologists are preventing, detecting, beginning to cure serious diseases, even the big leaguers like cancer, by taking part in the cell wars and winning. But theirs is not the only way.
Those technologies, however great they will be as we learn more about them, will not provide the basic cause of cancer, and that is why what is cancer and how is it formed and how can we actually cure it.
There are probably as many as 100,000 genes in human cells. each one the blueprint for a different protein. Some of those proteins form the tissues we are made of. Others, the enzymes and hormones, regulate our renewal, well-being, and growth. Recent evidence suggests that a few crucial genes can be altered, by cigarette smoke, for example, in such a way that they produce their proteins differently. Could these fatal switches, called oncogenes, cause the runaway growth of cells that we call cancer?
What my lab and many other laboratories around the world are trying to solve is the exact function of the chemical reactions that control cell growth, and therefore how oncogenes that are normally regulators of normal cell growth are altering the chemical reactions that occur in the cell. We hope we'll be able to provide enough information for the pharmaceutical companies to design high-tech monoclonal antibodies, for example, to block the action of these oncogene proteins when they're expressed abnormally.
The oncogenes bring incredible firepower to bear against the immune system defenders. An oncogene protein injected into a healthy cell makes it cancerous within minutes.
We are looking at the primary causes of cancer, that is the genes and the products, the proteins that they encode, that are causing this malignant form of growth to occur. So we somehow feel, from what we know today, that if we understand the role of oncogenes in controlling growth and causing cancer, we may actually solve precisely what is cancer.
Biotechnology's first forays into the immune system were controversial. Interferon failed to live up to the expectations heaped upon it. Interleukin-2 has yet to earn its spurs. But now the front is broader. Genetic engineering promises to produce better, safer vaccines. Monoclonal antibodies are transforming diagnosis and looking for a breakthrough in treatment. Cancer won't be conquered overnight, but careless talk about magic bullets has been replaced with guarded optimism.
We are adding to the armamentarium of weapons that we have to combat cancer, adding a series of non-toxic, relatively effective biologicals that I think in the next decade we're going to see many of the tumors, the dreaded tumors such as lung and colon cancer, suddenly become manageable diseases in the human population.
The recombinant technology and the biotechnology approach to this disease have been absolutely essential to our current information. Vaccine development rests on that approach. The diagnostics have been based completely on recombinant technology. And it's highly likely, I think, that the therapeutics will at least to some degree involve biotechnology as well.
The most significant aspect of this recombinant hepatitis B vaccine is the fact that it's the first one, and it provides a model from which other vaccines can be developed. It indicates really that very complex antigens, viral antigens, and eventually bacterial or parasite antigens can be made in microorganisms like yeast or bacteria in such a way that perhaps a lot of other vaccines will follow.
We're going to use monoclonal antibodies to remove unwanted cells, whether they're cells that cause graft against host disease or to remove tumor cells. We're going to use the lymphokines like interleukin-2 to help the body's immunity to destroy residual tumor cells, and we'll use the recombinant growth factors to accelerate recovery from the treatment.
Once we get over this idea that every new biological is going to cure all cancers, and we take the time to determine where its efficacy is going to be maximally demonstrated, I think then you'll see the sophistication and maturity of biotechnology companies, both in terms of their abilities, their expectations, and realization of their goals.
will the life revolution stop? Not just microbes, but large animals are now cloned, gene-spliced, and patented. Can human beings remain unscathed? We asked the human gene bankers and a human guinea pig. Who will benefit in future from genetic engineering? Will it be the sick or the shareholders? If the military control it, will there be a future at all? Join the life revolution to find out.